All right, there's the record button and share screen. And in particular, I want to focus on one thing today, and it has to do with groundwater and it has to do with this concept of recharge. And I mentioned a couple of these items the other day, but I think they're worth coming back to. And I want to show you an example from Google Earth that I think might help you understand this issue related to water and the western part of our country. So that's where we're headed, and it's this word Ogallala. Ogallala, everybody. That's an important word for today. So before we get there, I sort of glossed over this, and I want to make sure that this is something that is in your brain, and it's something that you probably have seen. Going back years, middle school probably, you saw this somewhere. And this we live on this planet that is it's sort of interesting when it comes to water because the majority of our planet is in fact water, but the amount of water that's actually available to us as humans to use in a way that is actually important to us is actually very small. And so this is a graph or a pie chart, I guess, that you should be familiar with. And the important thing is that only about 3% of the total water on the planet is available to us as fresh water. And then of that 3%, okay, a huge chunk of it is locked up in the glaciers, almost 77% of it, or just over 77% of it. And that changes as the glaciers melt and whatnot. But a big chunk of it, almost 3/4, is locked up in ice. The below ground part of the 3% is almost a quarter. And in this part of the world, that's really important. Okay. That's what we refer to as the aquifers. So, it's something that you should be aware of. That 3% number is a big one. Now, we talked all about this, but I do want to bring this little tiny thing up again, and I want to focus on this concept of recharge. And the recharge, see, my little cursor disappeared, but the recharge area that you see here in this picture on the top left, that's an important concept. And the idea with recharge is the idea that the aquifer is we have to replenish the aquifer. And so when it rains and that rain percolates or infiltrates into the ground, then that rainwater eventually makes its way to the aquifer, and that's how we recharge or we refill the aquifer. Keep in mind, the aquifer is not an underground cave. The aquifer is a layer of rock, usually, that is porous, and the rock fills with water. And then we draw the water out using a well. Okay. So this recharge concept is an important one. If you're taking more water out of the aquifer than is being recharged, then eventually you're going to deplete the aquifer. When that happens, the first step is to dig a deeper well. Okay. But at some point, it is possible that you can actually empty the aquifer. So that's an important concept for today. Now, we live in an extremely water-rich place on Earth. Okay, we are very lucky when it comes to water. We have plenty of groundwater and we have plenty of surface water. So our issue is not so much related to running out of water, but it's more related to contaminating the water. So but that recharge is an important concept. Okay, so we talked about all this stuff. This is the Ogallala Aquifer, and I want to take a moment and use this as an example of an aquifer that is being depleted. So in this picture, you can see it's basically the central part of our country, and this Ogallala Aquifer is enormous. And in this picture, you can see outlined in yellow, orange, and red how much the aquifer has been depleted. And so if we stop here now for a moment and we transfer over to Google Earth. And let's just consider this for a second. So first, let's just look at the geography of our country. And what should become immediately obvious is that the eastern part is very green. And if you consider the western part, it looks brown. And so let's break that apart a little bit here. So we know the Appalachian Mountains run from Maine all the way down into Georgia. And so when we look at the East Coast, the eastern, I don't know, 20% of the country, that green is really represented by forest land. And then as we move into what we refer to as the Midwest, starting in Ohio, all the way through Illinois, Wisconsin, up into the Dakotas, and all the way down into, Oklahoma area, the eastern part of Oklahoma, that green is represents mostly farmland green. There's forest in there as well, but a lot of that green is farmland. And then you can see that green kind of gives way to the tans and browns as we approach the Rocky Mountains. And so there's a pattern that's emerging here, and it's related to the direction that weather moves across our country. So if you want to know what the weather is going to be like in Verona in, like, let's say tomorrow, what you would do is you would look at what the weather's like in Iowa and Minnesota today. And then more or less whatever's happening to the west of us is going to move into our area tomorrow. So the weather moves from west to east across our country. And so there's a characteristic pattern that emerges when air masses strike mountain ranges. And what you end up with is, on the side the wind is coming from, you end up with a really green, lush environment. So if we consider the Cascade Range all the way down into the Sierra Nevadas, what we find is that along the coast of the Pacific Ocean, we have lots of green. The air mass hits the mountain range, it goes up over the mountain range. As it's moving up over the mountain range, the air cools, any vapor in that air condenses, and it falls out as rain. As the air mass continues to move to the east, it falls down the mountainside. And as air falls, it heats up, and that air tends to be hot and dry. And so we see that pattern emerging here, in particularly with the Rocky Mountains. So right about here is Denver, Colorado. Denver, Colorado is on the east side of the Rocky Mountains, and Denver, Colorado is considered mild and dry, very mild, very dry. And the reason is that air is coming down off the Rocky Mountains and it's heating up, okay? And it's blowing essentially on the entire eastern side of the Rocky Mountains, warm, dry air. What that results in is a fairly arid environment all the way up into, the northern part of the Rocky Mountains, all the way down into Texas. This is considered a dry area. As you move away from the Rocky Mountains, then the air masses tend to get moister, and the environment gets moister. So in this part of the country, now we're influenced by air masses that might blow all the way up from the Gulf of Mexico, or air masses that might blow down from Canada, bringing moisture with them. So what does that mean for aquifers? Well, let's take a look at Iowa. We're going to zoom in here, if Google Earth cooperates. Let's zoom in on Iowa and Wisconsin. And what you should start to notice, I'm going to make sure that I go nice and slow. What you should start to notice as we zoom in here is a grid pattern emerges. And Iowa is my favorite example to use of this, because Iowa is flat and Iowa is fertile. And so as you look at the screen, what you're seeing is a grid. And those grids are roads. And essentially the entire state of Iowa is divided into little 40-acre squares. And those 40-acre squares, that's how it was originally divided by the United States government when the early settlers and the early surveyors came across the West from the East. They took all of the land owned by the United States and they cut it into little 40-acre squares. And then they gave it away, by the way, for free, the Homestead Act. So when you look at Iowa, you see this pattern emerge. And if you zoom in on any given square, you will notice that the squares are divided into smaller fields. And those fields are planted from corner to corner. So we're just zooming in on some random place here in Iowa. This is a farm field. You can see a barn there. It looks like a barn. And it's taking a little, there we go. And that field is planted from one corner to the next. And so if you're a farmer in Iowa, you plow that field, you throw some seeds down, and then you just wait for it to rain. You got good soil and you've got good rainfall. And if you have a good year, you're going to have a good yield and you can harvest from the entire field. Okay, so that requires little to no irrigation. There are places in the Midwest that do use irrigation, but it's rare. That process essentially relies on nature. Let's zoom back out. Ta-da! All right, now let's consider what happens as we move west in the United States. As we move west, we can still farm, we still have decent soil, but the climate is different. The climate is drier. So how do we make farming work? We have to add water. Now, what you're going to see here is something very different and something quite remarkable. And I hope this gives you a visual, an idea of how you empty an aquifer. Okay, I'm just letting it zoom in. Now, can you see the pattern emerging? Take a moment. You should see a pattern emerging. In Iowa, we saw a grid. We saw squares. We saw rectangular farm fields. This pattern is circular. Do you see all the little circles? See all the little circles? Those circles represent farm fields. Let's zoom in on one. This is a good one here, I think. Okay, so this is what farming is like as you approach the Rocky Mountains. So this would be northern Texas all the way up into the Dakotas. And you can grow good crops, but you have to add the water component. So what you're seeing here is an irrigated field. And at the center of each of these circles is a hole in the ground. It's a well. And that well taps into the Ogallala Aquifer. All of these wells are tapped into the same exact aquifer. That well is then connected to a spray irrigation system. It's a long irrigation system on wheels. The wheels are mechanized. You push a button, the irrigation starts, and the wheels start to move. And so if you can imagine sweeping out an arc with the center point fixed, that's what you're seeing right here. So the water is sprayed and it ends up being in a circular pattern. Here's the important part. Look at the crop. The crop ends at the exact point where the water stops. So you have green crop where you add water, where you don't add water, it is brown. And so if you remove the component of water, you do not grow crops in that area of the world. Now here's where it gets impressive. Unfortunately, don't know if you're going to be able to really see this, but I'm going to go slow and just see if you can see this. So here's where it gets impressive. All of those circles are connected to the same aquifer, and every day they're spraying water. And so when we talk about this concept of aquifer level and recharge versus discharge, you can imagine how the Ogallala Aquifer has gone down by 90 to 100 feet. That's a lot of water, okay? And unless they reverse that process where the recharge of the aquifer starts to outpace the discharge, this aquifer will eventually dry up. Where it gets impressive is when I start to scroll. And I know this is a little slow on your camera. It takes a minute for Google Earth to process, but we could stroll like this all the way up into the Dakotas, and what you would see is field after field after field of circles. If you remove the aquifer, you no longer, I mean, it becomes very difficult to have agriculture in this area. And it just covers the whole area. Okay, so that's an example of this aquifer issue that's related directly to the aquifer actually eventually, disappearing. That's the biggest aquifer in our country, by the way. All right, so I wanted to hit on that because it is important. I think we talked about this stuff, but I also want to just show you quickly then how this works. We talked about the concept of the dams and the dikes and the levees. You should just know the difference between a levee and a dike. A levee keeps the river from flooding. The dike keeps the ocean out. There's a lot of other issues related to that, but the dam we did talk about and the concept of an aqueduct. Let me just mention one other thing with this before we get to the irrigation thing, and then it will be done. So this is a picture I mentioned of Lake Dillon. I used to live right at the bottom of that dam. Lake Dillon is a reservoir. So when you build a dam, there's always a function of the dam. Okay, people don't build dams just for the sake of building a dam. There's always some function. And the two main functions for building a dam, one is electricity production, and the other is to create a reservoir. And there are some real benefits to this. There are some drawbacks. So when you build a dam for electrical production, it doesn't require any carbon. It's a great way to produce electricity. So what you're using is gravity. So you build a dam, the river backs up and it forms a lake. Now you have a difference in elevation between the top of the lake and the river below on the other side of the dam. You poke a little hole in the dam, and in a controlled manner, you allow that water to flow through that hole. And as it's falling to the river below, you pass it through a turbine. You just make that water hit a turbine. The turbine spins and it turns a generator, okay? We'll talk more about how electricity is actually produced, but there's a basic physical law. If you take a magnet and you wrap that magnet in copper, okay, spin the magnet, you get the electrons to move. And once those electrons are moving, you stick a wire on it and you run those electrons to your house, and that's electricity. So the key is you got to get that magnet to spin. And so you can spin that magnet by just simply attaching it to falling water. The other thing that you can do with a dam is you can back it up, and now you have drinking water. And so in the case of the Dillon Reservoir, that's what supplies Denver, Colorado with its water. The negatives of this, you change the entire ecology of that river. When you turn a river into a lake, now you've changed the ecology of that space. So I want to mention this one in particular because this is a common ecological concept that's brought up. When you change the ecology, one of the things that you impact is spawning of the salmon, and you see this in the Pacific Northwest very commonly. Salmon they're an amazing species, and there's some peculiarities about that species. Wherever that fish is born in the river, they return to lay their eggs. How do they get back there? Mr. McCormick, how do they know where to go? So the fish are born in a river. They follow that river to the ocean. They mature as adults in the ocean. When they're ready to reproduce, they swim back from the ocean to the place they were born to lay their eggs. So if you put a dam in the river, obviously the fish can't get over the dam. So this is an example of how ecologists have gotten around that problem of dams. They create what's called a fish ladder. And so the river leads to the dam, and then along the side of the dam, there is a series of steps, and the fish actually jump up each step on their way to the other side of the dam. And so this is a way that ecologists have gotten around the negative impacts of putting a dam on a river. Los Angeles, New Orleans, they're all dependent on snow melt from the Rocky Mountains for their existence. And this is something that is going to become an issue, folks. In the next 50 plus years, actually, it probably won't even take that long. In your lifetime, this area of our country is going to be very water stressed. The Colorado River, if you look in the bottom kind of central part of this map, the Colorado River is supposed to drain into the Gulf of California. It just literally dries up in the middle of Mexico. So much water is pulled from that river, it no longer flows to the ocean. And there are about 40 million people that are directly reliant on the Colorado River for drinking water. And that's how you live in a desert. The way you live in a desert and you develop a city like Las Vegas, Los Angeles, Phoenix, is you pull water from the mountains. And that's the snow melt and the precipitation that falls in the mountains eventually feeds the thirst for that entire Southwest. That's going to become stressful in the next few years. Okay, the last thing I want to talk about is this concept of desalinization. And again, we've got this planet that's covered in water, but so much of the water is not available. So how do you make that water available? You have to remove the salt. The way you do it is just simply the old-fashioned way. You take salt water and you boil it. When you boil the salt water, the steam that comes off of the salt water is pure water. You condense that pure water and now you can drink it. The other option is to pass that water through a filter. The filter has pores that are so small that it only allows pure water through, and any impurity or even things that are dissolved in the water are left behind. Here's the problem with both of these methods. They take an incredible amount of energy. And so at this point, we do not have a method that is efficient enough to justify the use of desalinization for drinking water. There may come a point where that is necessary, but at this point, the input of energy is not viable for the amount of water that you get out. That's about it, everyone. Oh, irrigation, sorry. Last thing, everyone. Last thing, I promise. You should know these 4 types of irrigation. So the spray one in the bottom right-hand corner, that is the device that I'm talking about with the Ogallala Aquifer. You can see that the sprayers are attached to wheels, and those wheels move. And as long as you have water to put into that sprayer, you can go grow some good crops. The drip one, this is an important one. So the idea with the drip is you actually have a line, and that line is attached to water, and that water line has a little hole at each individual plant that you're planting. This is the most efficient way to irrigate because you are delivering water directly to the plant in question, okay? Spraying is considered the least efficient because you're spraying water all over, and there's a great deal of water that is lost to evaporation. Furrow and flood, you see the furrow very commonly in the West, and it's an interesting one. Basically, you take the Colorado River and you create a channel. So there's a channel that goes directly from the source of water, Colorado River, very common, and that channel then leads directly to the fields. You plant on a raised ridge, slightly raised above the furrow or the valley in the field, and you just drench the entire field. The water fills the furrows, and that's what feeds your plants. It requires a lot of water. The flood is a similar process, but instead of having furrows, you just flood the entire field. The flood is mostly dependent on the type of plant you're growing. Some plants can handle a flood, some can't. But all of these are examples of irrigation. Okay, I'm done. Sorry, everyone. That was a lot, wasn't it? I'm going to stop this. I'm going to stop this